Figured I'd just make a 5-minute video about rerouting. So the idea is if you have a tree and you're trying to figure out some quality about each of the vertices, let's say like the total, like I think the most basic case is like total distance to all other vertices. So if you're here, the total distance is going to be like 1 plus 2 plus 1 and blah, 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 blah. And you're going to get some answer. And then you want to find that, let's say, for every vertex. So if you did this naively, it would be probably O of n squared. Because you'd say, okay, like BFS out from here, I guess, or DFS, whatever you want to do. And then you'd get some answer. You get 1, 2, 3. You get 9 plus 6 plus 2. So you get 17, would be my guess. But you can do better than that, right? And the observation is that, well, if you know the distance here is, what did I just say? It was 17, right? Because 2 times 1 plus 3 times 2 plus 3 times 3. Then if you're checking here, you don't need to BFS out again and do O of n. We can just get this down to O of n total. This is just going to be O of 1 to go from 17 to whatever this number is, right? So what's this number going to be? This number is just going to be, well, let's say we're here. We know that everything this way is going to go up by 1, and everything this way is going to go down by 1 in terms of like the distance that path is contributing. Because when we step from here to here, we're saying like, okay, everything over here, including the node we just stepped out of, all of this now has to also traverse through this edge. But then on the other end, like these two, both of these don't have to traverse through this edge anymore. So if we just go through that math, we can see like, well, that's 1, 2 things that don't have to go, and 1, 2, 3, 4, 5, 6, 7 things that do have to go through that edge. So our answer then, let's clean some of this up, is going to be, I don't know what that is going to be, what's this, 22. And if we just quickly mentally check, we got 2 have to go a distance of 2, plus 1 has to go a distance of 2, plus 2 have to go a distance of 3, plus 3 have to go a distance of 4. So what's this, 18, 20, 22. So we can kind of corroborate that, right, by just doing the BFS anyway with this one. So we can see like all we really had to do was just say, okay, well, how many vertices are in this subtree and how many vertices are not in this subtree? And then this amount goes up and this amount goes down. And if you think about it, really, like the reason why people like to call this rerouting, at least I've heard that term before, is because, let's get rid of some of this, because really what we're doing is we're kind of saying, okay, well, what's the distance from the root to all the vertices? I mean, it's all, we're doing a bunch of, you could phrase it however you want, but a way to phrase it that I think is pretty compelling is to say, what's the distance from the root to all the vertices? Okay, that's good. If we know that, we have an O of 1 transition to what if this was the root? And if this was the root, let me put the O of 1 here. What we're saying is now we've kind of changed it a little bit. And now let's say this is node 0 and this is node 1. Now we have node 1 here and node 0 here. And what's happening? Then we've rotated this a little bit. So we have something like this. We got kind of a red-black tree thing going on. Okay, and now we have this. So now we're asking the same question, but with this as the root. I guess that's the idea behind why people call this rerouting. It's very similar to tree DP, which you could argue that's exactly what this is. We've established a transition, and we've said, okay, DP at 1 is equal to some sort of function on DP at 0. But I think tree DP is generally refers to like an example would be like a maximum matching. What's the maximum matching? Like number of edges where you don't ever take any adjacent edges. They never share any vertices. Well, you're going to kind of That would be an example of tree DP, and it's kind of similar to rerouting in a way. You could argue it's the same. But it would have a slightly more complicated transition. This has a pretty basic just O of 1 transition from a given node to a given adjacent node. Whereas tree DP, for example, like if there was like another edge here, you'd say, okay, well, it's going to be the maximum matching of like this and this and this plus some choice of which of these edges you take, if any. It'd be something like that. Just to give a sense kind of in the geographical layout of algorithms, like that's an adjacent term. But anyway, back to rerouting. So we start with the root, let's say node 0, and then we go down here, and then we go down here, and you can imagine that would just be, you know, a tree where we're then starting here. And then what do we do? Well, we go back up. So if we wanted to get, like, eventually we're going to need to calculate this vertex, right? Like, what if this was the root? Let's get rid of that because it's not part of it. Well, what we would do is, right, we would go back from this tree layout, this root, we would go back up in O of 1. And then we would be here again, and then we would go back down. Yeah, so the only like tricky part, I think the thing that makes this not seem super apparent, because for me at least, like when you see this O of 1, it makes sense. Like all you did was just 17, you took away 2, of course, because you have 2 nodes you're getting closer to. You added 7, of course, because you have 7 nodes you're getting further away from. Great. But like, I think the reason why this doesn't feel super apparent at first is because there's actually kind of an extra data structure you need to make it O of 1. And what you need is like the population in a subtree. Like, how do you know in O of 1 that this is 2 and this is 7? Well, you can just kind of have an inclusion exclusion, like pretty basic. Okay, the population of this subtree is 2. The population of this subtree is 9. Like everything. The population of this is going to be 6, right? This is going to be 1. And then for any given vertex, when you go in, like if we were here, we would have 17 and we would say, okay, the population of this whole subtree is 6. So we're getting further away from 9 minus 6 is 3 things that are in the tree at all that are not in this subtree. And then we're getting closer to 6. So we would say minus 6 plus 3 is equal to 14. 1, 2, 3, 1, 2, 3, 4, 3. Yeah, that's right. Yeah. So that's the basic idea. We just need one auxiliary data structure, which is like population at U is like number of V in U's subtree. And then we're good to go. So I'll run through an example quickly. For this one, total sum of interaction cost in tree groups. It's basically saying you're given a tree, every vertex belongs to a group. What's the sum of distances for every node along, what's the sum of distances from every node to every other node in its own group? And we can just immediately scroll down to the constraints and see, okay, well, the groups only goes up to 20. So 10 to the 5th times 20 should be completely fine. So we can just keep track of this distance metric, but for all 20 groups. So it's a slightly more complicated problem, but if you have this in your pocket, then you know it's not inconceivable to extrapolate it. So I'll just code it out quickly. Let's build the adjacency list. So okay, and then I'm just going to pre-calculate the population of every subtree. You could probably do it all in one DFS, but I'm just going to DFS through, find the population for everything, and then I'm going to do this DFS where I say start with distance at 0, transition to this distance, transition, and then transition back, and so on. That's what I'm going to do for clarity's sake. So, and I'm going to do it iteratively. So I'm going to say stack is equal to 0, 0, 1. And what I mean by this is you're at this node at a given state. This is your parent node, which for node 0, it's the root. So I'm just going to say it's its own parent node. And then 1 means you're going down. 0 is like you're going back up, which is when we're going to recalculate the population given the already calculated populations of the children. So u parent direction equals stack.pop. Let's see, so here we want to say for v in ADJ u, if v is parent, continue, because we want to ignore that. For I in range, and I'm going to have a limit that's just like how many groups are there. I could just say it's 20, but that's fine too. Population at u at I plus equals population at v at I. And then I also want to say population at u at its own group, right? We have to contribute it as well, plus equals 1. So I need population. And then I also want that initial distance. We need to like actually calculate, okay, what's the initial distance here? 17. We can just BFS that one specifically. Everything else is a transition based off of that, or a transition based off of something else. But to get the original one to actually transition from, we can just find that initially. So I'll just have distance is 0 times lim, so the distance to every element of every group. And then that'll just be something like distance at u at, distance at I plus equals population at v at I. We now have this edge from everything in V. Okay, we have to remember to go back up and then recurse to children. VU1. Okay, and then I'm just going to do another DFS. I think that's fine. So stack.append while stack. I'm going to have res if d equals 0, continue, stack.append up1, up0. VU1. Okay, and then here the idea is this is where we're going to step into a subtree. And then this is when we're coming back out. So this is when we're stepping out of a subtree. And first things first, I'm just going to say if I'm already in the whole tree. I'm already in subtree 0. That's the way I've set this up. You could easily get rid of this if statement and just have res start out as like groups at 0, but that's a tiny little small optimization that doesn't matter. So if then we want to step from wherever we currently are into this subtree. So it's going to be, let's go to a clean tree. If we're here and we're going to step to here, this is going to be population. This is u. So it's going to be population at u, at I for all of the, but that's fine. Population at u, just for any group, it's going to be population at u is now decreasing, right? And then the population of everything else is increasing. So what is that? Population at 0 is going to be the population of everything, minus population at u is going to get us everything that's not in our current thing. So this is just going to wind up being population at 0 minus 2 times population at u. And then we're doing that for every single I, right? That's kind of the twist with this problem. And that's the amount that the distance to everything is changing when we step in. And then when we step out, it's just going to be the opposite of that. So, oops, I want if u here. For I in range lim dist plus equals population at 0 minus population at u at I, forgot about that, times 2. Res plus equals, and then we should hopefully just be able to say dist at group at u. And then to step out, it's going to be the exact same thing, but we're like taking it back. We're just reversing it. And so I'm going to click run and it's all going to be wrong. I got a little C++ism in here somewhere. Max group. Int object is not iterable. Oh, I said dist. I want dist at I. Okay, same here. Okay, so it's wrong, and we can see we're double, and that's because we're taking for every node the distance from that node to every other node in the same group, but that means we're double counting paths, so we can just say over 2. And there it is. It's not the fastest ever because we did 2 DFSs, but that's proof of concept, and all these are pretty similar. So that's the idea behind rerouting.